We'll get right into it. Okay, so I hope you guys had a good weekend. We have concluded and actually finished part one of the Science 10 chemistry unit. So there are three parts. Part one is for sure the easiest part. It's also the quickest part, and it is probably the part that I think segues best into these other two parts. I was looking through the outcomes again, and for Science 10, there are not a lot of outcomes that we've actually covered in that first Science 10 part. A lot of that is just making sure that your skills are up to date and making sure that when we're talking about and having all these future conversations, the stuff that we're doing makes sense. So my intention is for us to be able to get through all of part two and part three throughout the month of May here. We lost a bit of time with those 2 weeks that we lost due to the coronavirus here. And it seems like we are going a little bit slower in terms of the content. So I want to make sure for sure that we get through chemistry. And then if we leave a little bit off of the physics unit at the end, I'm not super concerned. Getting the chemistry stuff done is more important than getting the physics stuff done, just in terms of like physics 30, chemistry 30, so on and so forth. So the first thing that we're going to talk about here is last time we were talking all about Bohr diagrams. And Bohr diagrams are great, but they're limited in the sense that they only really work up until calcium. After that, if you go any higher in atomic number, the Bohr diagrams do not work and they are not accurate. But what Bohr diagrams will be used for is they will be used to kind of give you an idea of what's actually happening at a chemical level. So this particular PowerPoint deals with two different types of compounds. We're going to talk about ionic compounds and molecular compounds. Every kind of substance that you think of is made of a bunch of different elements, or it's made of a bunch of different compounds. The examples I have here are water, air, hair dye, bleach, medicines, vaccines, food. All of those different things are made of compounds, and it's just different combinations of those compounds, or putting them in different locations or making different shapes with them. Compounds, what those are they are pure substances made of two or more elements that are chemically combined. When you did your flow chart last week, you would have been able to see that this is true. So water is hydrogen and oxygen, and then hydrogen peroxide, which is what you use to make elephant toothpaste or clean out a wound that you have, is also hydrogen and oxygen. And so this is my favorite meme of all time, one of them. This guy, they both enter a bar. This guy says, I'm a chemist, I'll just have some H2O. This guy says, I'll have some H2O too. The bartender serves them, they both drink, and the guy on the right dies. And the reason is that water has a chemical formula, you probably know this one, of H2O. That's what the chemical formula of water is. Hydrogen peroxide, and the reason this guy's comment is really funny, hydrogen peroxide is H2O2. So they have the exact same elements in them, but a different number of those elements. So hydrogen and oxygen in the water case, we have two hydrogens, and because there's no number right beside this little oxygen here, we would say that we have one oxygen. With hydrogen peroxide, we have two hydrogens and two oxygens, and as such, it acts like an entirely different element or an entirely different compound. It's not even the same. So the two types of compounds that we are going to talk specifically about is ionic and molecular. Today we are going to focus mostly on ionic. So we're going to finish this general PowerPoint, and then we're going to go more into ionic compounds and how those look and how those operate. Molecular compounds tend to be a little bit trickier to name, but also to understand, and so we'll talk about those second. Ionic compounds are pure substances that usually consist of one metal and one non-metal. So usually what I write when I write ionic compounds, I say a metal plus a non-metal. Metal plus a... Oh, it doesn't let me undo. That's very interesting. Is that my eraser? That is. Metal plus a non-metal equals an ionic compound. And I'll use these M's and NM's to label what are the metals and what are the nonmetals. But generally speaking, ionic compounds have the following properties. They have high melting points, they form crystals, they dissolve in water, they're solid at room temperature, and they conduct electricity. So most of the bottles of chemicals that I have in the back room of our little science room there, most of those are ionic compounds. They're solid. I can dissolve them in water and make different aqueous substances. Aqueous just means it looks like a liquid. And that's kind of basically all the compounds that I have back there. So this becomes an incredibly important slide here. All of the metals are labeled in this purpley pink color. So all of these guys with the purpley pink color, these are all the metals. All of the non-metals and the noble gases are green. And so what's going to happen in an ionic compound is we're going to have one metal and one non-metal, and they're going to be coming together. The ones that have this shaded region like this, that means they have dual properties, meaning they could act like a metal, they could behave like a non-metal. What we'll talk about in a sec is just how that looks in terms of giving up or receiving electrons. That generally defines whether something is a metal or a non-metal. So to form an ionic compound, atoms must gain or lose electrons to form something called an ion. We said an ion is anything with a charge. Anything with a charge. Metals lose electrons to become positive. Nonmetals gain electrons to become negative. If you've done the element behavior assignment, that was exactly what we were talking about. Metals lose electrons to become positive. Nonmetals gain electrons to become negative. So an example of a metal losing an electron would be lithium, for example. So this guy up here, lithium. We said that that is in the very first column. So we know it has one valence electron that it wants to lose, and it will gain a +1 charge. Nonmetals gain electrons to become negative ions. So again, everything in column 8 here, these are the noble gases. So they don't want to gain or lose or have any sharing of electrons at all. But these guys do in column 7a, which on your periodic table looks like column 17. And so I'm going to choose fluorine, which I know has 7 valence electrons, meaning it wants to gain one more electron to fill that outer ring. And so fluorine would have a -1 charge. If you've thought ever about magnets before, magnets are a positive charge and a negative charge coming together and sharing their electrons back and forth to basically stick together. That is, at a chemical level, what is happening between different elements. Lithium's positively charged, or it wants to become positively charged. Fluorine wants to become negatively charged. And so there's a perfect relationship there, like a magnet, where those two have opposite charges. They're going to attract each other, and they're going to try and form a neutral compound or a bond with each other. So these two, lithium and fluoride, are going to come together, and they're going to share their charges with one another so that their overall charge is 0. Overall charge is 0. I actually want to do this example with you. I want to walk you through this. So we're going to look at two different compounds. We're going to look at sodium and we're going to look at chlorine. First thing I need to do with both of these is I need to draw their Bohr diagram. So for sodium, I'm going to do my little PEN. Sodium has an atomic number of 11, so I know that there will be 11 protons. Its number of electrons its number of neutrons will be 23 minus 11, which gives me 12 neutrons. And then the number of electrons, normally we would say this would be 11 as well. And then when we're looking at chlorine, we'll do its pen as well here. We say that chlorine has an atomic number of 17, so we know that normally it would have 17 protons and 17 electrons. Its atomic mass is 35, and we would subtract 17 from that and get a number of neutrons equal to 18. So if we were to draw both of these guys, if we were to draw sodium here, I would draw my nucleus, and I would say P plus is equal to 11, and with the circle, the number of neutrons is equal to 12. And then I would know I need to start drawing 11 electrons. If I'm using my little cheatsy doodle tactics here, I would know that I need to draw 1, 2, 3 rings for both of these. They're in the third row, and so I know that they will need 3 rings. So my first ring then would be able to, I'm going to draw my 3 rings. 1, 2, sorry, these circles are really bad. And then I would know that I need to put 11 electrons. So I know that this first orbital can hold 1. Oops, sorry, that's the wrong orbital. I know that this first orbital can hold 2 electrons, so 1, 2 electrons. I know the second orbital can hold 1, 2, 3, 4, 5, 6, 7, and 8 electrons. I could count up and see that I've drawn 10 out of 11 electrons, and I'm going to draw my 11th electron right here. So that's what sodium looks like. This is what sodium looks like. And then in black, I'm going to draw chlorine. So again, chlorine, draw a ring in the middle. P plus is equal to 17. N, the number of neutrons, and circle is equal to 18. And again, using my little cheatsy doodle strategy, I could look at this and say chlorine's in the third row. It's in the third row, and as such, I know I'll have to draw 3 rings. So first ring, second ring, third ring. So my first ring, I know it can hold 1, 2 electrons. My second ring, I know it can hold 1, 2, 3, 4, 5, 6, 7, 8 electrons. I've drawn 10 of my 17 electrons. So I'd have to start drawing the 7 on the outside. So 1, 2, 3, 4. And then I'd start pairing these up. 5, 6, 7 more electrons have been drawn. And so when we were looking at this last week, we said, okay, this is great, but we know that these orbitals want to have full valence shells. They want to have full outer rings. Or we called those valence shells. And so with both of these, we can see that we're unsatisfied with this outer ring right now. So on sodium, we can see that we have 1 valence electron. And so with sodium, we can either give up 1 electron or we can receive 7 electrons. And we said that we don't want to do this second option because that requires way too much energy. We want to do this first option where we give up 1 electron. With chlorine over here, we have 7 valence electrons. So we can either receive 1 electron or we can give up 7 electrons. And again, we said whatever number is lower in this choice is what we want to go with. So we would rather receive 1 electron than we would give up a whole bunch of electrons. So I'm going to erase these 2 options because we know they are not true. And so what we can then see is we can see that we have the perfect situation. We have the perfect situation for these 2 to date. We have 1 electron over here that it wants to give up, and specifically it would like to give up this electron. And then on the right hand side with the chlorine, we can see that it wants to receive 1 electron. So if this one wants to give up an electron and this one wants to receive electron, well, that seems like a perfect situation for these 2 to form a bond together. And so when they do, I'm just going to go back 2 slides here, back 1, 2 slides. When they do, you can see that this electron here is going to totally go over to this chlorine. It's going to be totally given over to this chlorine. So what I'm going to do is I'm actually going to erase this one here, and that red electron is actually going to travel right over here and come and join the chlorine over here. And so now what's happened is our number of electrons in both of these has changed. Chlorine's gained another electron. So rather than it having 17, it now has 18 total electrons. And rather than sodium having 11 electrons, it has 10 electrons because it lost one. And then what we said was that whenever something loses a negatively charged electron, it's like losing one negative charge. So this one has more protons, more positively charged protons than it does negatively charged electrons, and it has one more, so it's going to have a charge of +1. Chlorine now has one more negatively charged electron than it does protons, so this will have a charge of -1, like this. And what we'll eventually see is that when these two come together to form a bond, they're going to create something like this, NaCl. We said Na was sodium, Cl was chloride, so this now becomes sodium chloride. That's its full name, sodium chloride. In the next PowerPoint that we do, we will talk about how to actually name these ionic compounds and how to come up with this chemical formula, because it's not always that simple. Does anyone have any questions so far? Cool. So this is some more of that ionic compounds practice. The idea with this is we want to be able to look at the atomic numbers that exist here, the number of protons and the number of electrons and the overall charge. So with all of these, you can actually see what the overall charge is. So for this first one, calcium is a +2. This one has a bromine has a -1. This Fe, this iron has a +3. Oxygen has a -2. Zinc doesn't have any charge written up here, so that means it has a charge of 0. Copper is a +2. Magnesium has a charge of, Magnesium doesn't have any number written, so it has a charge of 0. Again, it has nothing up here. The next one, however, wow, I'm clicking buttons all over the place. The next one, however, does have a charge. This one has +2. So that means that version of magnesium has given up 2 electrons to get a +2 charge. So we'll do this first example here together. Calcium has an atomic number of 20. So I know that that means it has 20 protons. And if it has a +2 charge, that means it's lost 2 electrons, meaning that this one would only have 18 electrons. If we are looking then at bromine, which is the next one, bromine is over here, right here. It has an atomic number of 35. Bromine has an atomic number of 35, so that means I know it has 35 protons. And this one has actually gained 1 electron, meaning it has more negatively charged electrons than it does protons. So we would say that this has a number of electrons equal to 36. We'll do one more together. The next one that we do together here is Fe. Fe has a atomic number in the middle here of 26. 26. So that means I know that it has 26 protons, and it has a +3 charge. Because it has a positive charge, I know that it has lost 3 electrons, meaning that it would only have 23 electrons. Oh my word. Have I not been streaming this at all? Oh, that's horrible. Wow. Okay, good job, me. You guys didn't want to say anything? Sure. Yeah. Okay, wow. I guess I'll go back and do this example again. I recorded. Okay, did I stop the recording? No, I haven't. Okay,